Okay, guys, this is the second try to get this idea of um, induction. Let me just see that you can see me well. Yeah. I hope you guys watched the first session because it's not an easy idea, and that's why I'm doing it second time. So if it's your first time, it's going to be a difficult one. But just watch it again, that video and the other video, and hopefully it will work out. So we use induction to prove things. This is now we're in the domain of pure maths, and we want to prove a statement. For example, what we're going to prove now is that if we take the sum of the numbers, let's say 1 times 1 minus 1 plus 2 times 2 minus 1, or in other words, we'll make it simpler. Okay? So if I take 1 times 0 plus 2 times 1 plus 3 times 2 plus 1 plus 4 times 3, okay? Ba 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 ba, okay? Let's say up to, let's say, 15 times 40. Let me see what I'm doing here. Some kind of pattern. I want to prove that this thing is basically 15 times 15 squared minus 1 divided by 3. I need to prove that. That's a certain statement. Okay? And in fact, we've done that, or we used that. We didn't prove that. We used this formula, okay, last year when we did the Riemann sum. So we're going to prove it. Okay? Now we're using induction. What is induction? Induction is made out of 3 steps. I'm going to read to them again. I'm going to show you Olivia's domino method again to think about that, and then we'll do it. So the first thing, let me start with this. So let's say I have these 5 pins. Okay? And let's say I want to prove that I like them all. But let's say I can't prove it in the same, all of them together. I can't say I like them all. I can say I like this one. Okay? So how would I do it? How would I prove that I like them all?
You prove that you like one.
Okay, but before we know the idea, the most sensible thing will be to say what? I like this one, and 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 I like this one. Prove, okay? But let's say we have 5,000 before we go to it. Let's say I have 5. So to go, I like this, it's going to take a long time, right? So there's another way of doing it. What is it, Olivia?
You prove that you like the first one.
Yes.
And then you prove that
if you like
one, the first one, you like the one that's next to it.
Exactly. So I need to say, I like this one. In fact, I can say about any one of them, but we will start always with the first. So I'll say, I like this one, and if I like a pen, then I also like the pen next to it. Yeah. If I manage to prove it, I need to prove it. But if I manage to prove that if I like a pen, I like the pen next to it, then I'm done, right? Because I like this one, therefore I like the one next to it, which is that. But then if I like this one, which is next to it, this one, and then I can have another 5,000, in fact, infinite number of pins, like Olivia said, and that's proof, okay? The idea of proof is very, very important in maths, okay? And it's not something we use in day-to-day life. We kind of say, it makes sense, and it must be right. But that's not the same in maths. You have to prove it, okay? So, how does that work? Okay, so we need to prove that if I sum all the numbers between 1 to n could be, like I said here, 15, or it could be 10,000, it could be anything, okay? Therefore, those numbers, like I'll write it again, okay? If I have, let's say, 1 times 0 plus 2 times 1 plus 3 times 2, up to, let's say, we'll do another number, 21 times 20, then what would that be equal? Just to make sure you understand what I'm saying. According to this formula, what should it be equal? Okay, that's your n, right? Or your r. R goes all the way from 1 to n. So what is n in this case? 21. Okay? So it's going to be 21 times. Okay? Sorry?
Yesterday's formula.
It was a different formula. Last time I proved another formula. We're proving different formula today. But we're using the same method. Okay? So I want to prove that. So the first step is to check for n equal 1. Okay? So let's check for n equal 1. What does that mean? R from 1 to 1, n equal 1. Right? So I want to see what does that mean? What is that sum? This is sigma. You guys just told me about sigma. You saw me work with that in core maths, okay? That means that R goes from 1 to where? To 1. So in other words, it's just 1, 2. So that's equal to R equal 1 times 1 minus 1 is 0. Okay? And then there's no other R's. I don't have R equal 2, R equal 3, because that's it. We stop here. That's what that sigma means. We start from 1 all the way to n, which is in this case just 1 term. So that is equal to 1 times 0, which is 0. Okay? Now, we got to check on the other side. We got to check this side of the formula. Okay? So, in this case, n is equal 1. So, it's going to be 1 times 1 squared minus 1 divided by 3. 1 squared minus 1 is 0. I got 0 again. Okay? So, that works. I checked for n equal 1. Okay? I'm just going to pause here. Make some space. Okay, so we've done the first step. We checked for n, that's true for n equal 1. That's an easy step. It's an easy step. Okay? The second step is also easy. We assume for n equal k. Okay? So k could be any number. We tried for n equal 1. Now k could be, let's say, 17. So we just assume it for n equal k. What does it mean to assume? We substitute. Everywhere it says n here, we will put in the k. So we assume that that r from 1 to k, I substitute instead of n, I'll put just basically assume that true, should have done that, true for n equal k. Okay? So k r minus 1 equal n is equal k, so it's k times k squared minus 1 over 3. We assume that. Okay? These are two first steps and they're pretty easy, so you should score. I mean, induction is not easy, but the first two steps are easy. It's the third step that is difficult. Okay? So I'm going to write it down here because it's going to take us a while. So we need to prove equation true for n equal k plus 1. Okay? Now that's where the work begins. Okay? And there's different strategies, and this is where you're learning to kind of how to do it. Okay? I'm just going to quickly check how I've done it. Okay, right. Okay. Where did I start? Okay. So what I'm going to do, I'm going to start by writing what do I need to prove. Okay? Or what do I start? I start on the left side. I'll start from r equal 1 to n. But what is n equal now? What do we need to prove? N is equal to? Not k, k plus 1. We assumed it was true for n equal k. Now the n is actually k plus 1. Okay? Now I'm going to start on this left side where putting n equal k plus 1. And I will somehow need to get to this side, but instead of n, what would be written there? Not k, it will be k plus 1. So I'm going to start from that. Somewhere along the way, use this, which I assume is correct, and then hopefully get to that with k. I'll write it down. I want it to be no, don't want it to be k. I want it to be k plus 1 times k plus 1 squared minus 1 divided by 3. That's where I want to get to. Okay? Now, actually, you know what? Thinking about it now, this is already something that I can kind of do with it, right? It's like, you know, you want to do something, you look at it, there's something you got to do, right? There's a bunch of stuff you need to do, right? You can do, I don't know, factorize this.
Yeah.
K plus, yeah? So let's just do that, and you'll see it will help us later. So I'll leave that k plus 1 there. What is k plus 1 squared minus 1?
K plus 1 minus 1, k plus 1.
That's it. So k plus 1 times k plus 1 minus 1, all that divided by 3. Okay? And I'll write it down here. That's equal to k plus 1. Let's write it like this. K plus 1 minus 1 is k. Then I'll write k plus 1 and k plus 2. divided by 3. So I need to show that from here, I'm either going to get to that, or to that, or to that. And if I get to any one of those, obviously I've got it right. Okay, it's good to know where am I heading. Okay. Okay. Now this is again something you've never done. Okay, I'll just pause here for a second. Okay, so just to kind of clarify what's happening here, I'm going to put some squares and stuff. This is what we assume, and therefore this is what we're going to use. This is like our tool. You know, if you want to do a job, cut some grass, use the weed eater, that's what we're going to be using. What we want to prove that this is correct. But now we wrote that and we thought like, okay, we can do something with it. We opened it, or we actually factorized it, and then we got that, and then we just neaten it up. So this is what we're going to be looking for. This is what we want this to be equal to. Now, this is the trick that we have here. So we've got a sum, okay? R runs from 1 all the way to k. I want to break it into two sums, or a sum of two terms. The first one, I'm going to let R run from 1 to k. Okay? So imagine, yeah, it's just, this R just runs from 1 to 2 to 3 to 4 to 5 to 6 to k. And then to what will be after k? K plus 1. So I'm going to split this into two terms. From 1 to k. And then what will be the second term? That's the tricky bit. I'm going to pause, let you think about that. Okay. So what you guys discovered together with a bit of my support, that this term really here includes R equal 1, 2, 3, all the way to k. But I'm missing one more, and that's when R equal k plus 1. So I need to add, that's not complete. This is all the stuff here except for the last one, where R equal to k plus 1. So instead of R, I'm going to put k plus 1. So k plus 1, that's R, time, what is R minus 1 then? If R equal k plus 1, what will be R minus 1? Okay. Okay? Alright, we're there. Moving back to here. Okay. I'll pause again. Okay. So why did we split it? Why did we actually split it? And this is where your instinct needs to kick in, and you obviously only get that with experience. That this sum, we want to get rid of it. Because look, we start with something that has that sigma, and we need to prove that it's equal to this thing. There's no sigma here. So we want to get rid of the sigma, isn't it? That's what our motivation, to get rid of that sigma sign.
We use our tool.
We use our tool, exactly. That's why I wanted to split that into something that has our tool in it. And it has. This is the same thing as that. So instead of this, I'm going to write this thing. Okay? So that's equal to k times k squared minus 1 divided by 3. This is this bit. Plus k times k plus 1. And from then on, it's easy stuff. That's just normal maths core stuff. I'm doing it with my grade 10 now. Okay, factorization, right? Okay, so I'm going to put them all on under 3. So something divided by 3, which makes sense because I need to have all the 3 here. Okay, hang on, I'm just going to pause for a second to see how you guys are doing. Okay, so yeah, so I'm going to put it all on 3, and what I'm going to do now, I'm going to factorize this one. So that's k plus 1. K minus 1, right? K squared minus 1. There's a grouping there. Plus, don't forget the 3. There's a 3. Should I have a 3?
Yeah, 3k.
Yeah, 3k times k plus 1. And I'm almost there. I'm almost there. I just want to make sure you can see it. Yeah, you can. So I'm going to go down. Now, let's just run here. Okay? So I've got, what can I get out? K times k plus 1, all divided by 3. We're pretty much there, isn't it? K minus 1, k minus 1 plus 3, plus 3. Alright? K minus 1, so I can time it by that, and here I have a 3. And then I'm done, really. Alright, what do I need to do? What is k minus 1 plus 3? It's plus 2. K plus 2, which is just what we wanted to show. Okay, so I think the difficult thing in induction, one of the difficult things is to know when you actually proved it. Because you do so many things and eventually, okay, yeah, I proved it. See, I wanted to start from here, where n equals k plus 1, and I want to show it's going to be equal to the ring. Proved. Okay, pause here. We'll do one more example, but first of all, okay, so I think at this point, I want to, you had the question here, what about that thing in red, and why did we do it? So this is again another, I don't know if you get it sometime in trig, when you have to prove that the left side equals the right side, and then sometime you'll just go from the right side, get to the left side, right? But sometime you move the left side to something, and then you move the right side to something, and slowly you meet somewhere in the middle. You know what I mean? That's what we've done here. Okay? We needed to prove, okay, that when we put k plus 1, we will get this bit. We just substitute, instead of n, we substitute k plus 1. Okay? If I put n equal k plus 1, then I must put n equal k plus 1. I need to prove it. So when I just substitute that, I got this. Now this is like something that will be very difficult to get. I can go carry on and get there backward. But in this point, again, we thought, okay, let's just open it up a bit, open it up, and then we got that. And we got the red. Okay, Larissa, that's your question now. So we got the red. What is the red? The red is where I need to get to when I start from the left side. And eventually we did. We didn't use it, we just needed to get to it. What we used is the green. That was our tool. Alright, so I'll pause and move on to the next example. Okay, guys, here's another formula. This is our last example, a formula that we need to prove. And I chose a trig formula that actually is very useful. You use it a lot. It's called the Noirville formula. I guess that's the guy who kind of proved it. And yeah, so basically cosine theta plus, what is this I business? What is I? It's a preparation for our next lesson. So, okay, I square root of minus 1. Okay, that's a whole next week. We're going to have fun with that number. Okay, so I sine theta. If I power it by n, then all I got to do is cosine n theta plus I sine n theta. Very useful formula. Okay, just to give you a comparison, one of the biggest mistakes that up to grade 12 a lot of people do. Maybe you can tell me what the mistake they're doing. What is x plus y squared? Tell me what's the mistake that people do, not what's the right thing.
They don't do trinomial. Oh yeah, they just.
What would I write?
So they would say x squared plus y squared.
Exactly. Okay, and you know obviously it's not true. Right? I hope you know. Okay, obviously we've got that 2xy. Okay. And then, so a lot of people will say also x plus y cubed, oh, no problem, x cubed plus y cubed kind of thing. Obviously it's wrong, there's a whole lot of mixed terms going on. So this one, if you think about it, it's actually a very powerful formula. Because, if it was, let's say n is equal 12, let's say n is 12. Now, if you think about it, that means there's 12 brackets there. And it will be cosine power 12. Cosine times cosine times cosine is 12 times. But there should also be cosine times cosine times sin. There's so many terms there. You understand what I'm saying? This formula then makes it very easy to calculate. So don't worry about it. Simply cosine, this was 12, let's say. Then it just tells you, okay, that's cosine 12 theta plus I sine 12 theta. How easy is that? Instead of opening up all the brackets. And what we're going to do now, we're going to prove it for any n. Okay? So our first step, what are we going to do? Check for n1. Okay, so let's have a look. That's very easy. Okay? Cosine theta plus I sine theta power what? 1. Okay, well, what is that equal to? It's cosine theta plus I sine theta, which obviously is equal to cosine 1 times theta plus I sine 1 times theta. See what I'm doing here? That 1 is again is the n. You understand the first step? Very easy. First step is easy. First step is usually easy. Okay, done. Next then, what do? We assume correct form n equal k. Okay, so what does that mean? That means I write cosine theta plus I sine theta power k, yeah, equal to cosine substitute n equal k. So what should I write? Cosine equal? Instead of n, we're going to write k. So cosine k theta plus I sine k theta. Okay, we assume that. Now, again, so the first two steps are easy and you should get the marks there. Okay? You should get the marks. 3 is prove that. What should I prove? You guys tell me what to prove. I'll start you off. Cosine theta plus I sine theta to the power of k plus 1. In other words, you got it. We prove for n equal k plus 1 equal to cosine. Put brackets here, by the way. Yeah, what should I write in front of the theta? K plus 1 theta. Put fancy brackets. Plus I sine k plus 1 theta. Okay? Okay, I'll just pause here for a minute. Okay, so we pause here for, let's pause here for a minute and think again what we've done. What we need to do. We need to prove this in Wiesel formula. Okay? For any n. Now, we checked it for n equal 1. We got it. Not a problem. Easy step. Then we assume it. We just write it down. Instead of n, everywhere it says n, we put k. So we put it here, we assume it. That is what we call our tool. Okay? Remember, in our language, we call it our tool. We are going to use it in a minute. Now here I wrote, I'll write it in red, what we need to prove. We need to prove this one. We haven't got it, but we need to prove it. And what do we need to prove? Basically, I'll put, instead of n, I'll put k plus 1. So there's k plus 1 here, k plus 1 here, and here. Okay? So we start from the left side and get to the right side. In this case, I don't need to open anything. I mean, you can do k theta plus theta. No, I'll leave it like that. It's better. Okay? You'll see why. So I've asked you already, what's the first step? And Olivia realized very well that, because I mean, what do I want? I don't know what k plus 1 is. I don't have the exponent of k plus 1, but I know what it is with k. Okay? When I have it with k, I basically got rid of all the brackets. What I'm trying to say is, I have some brackets here, but I don't have these brackets here. So I want to get rid of them. How do I get rid of them? Use the tool. But the tool has an exponent with k, not k plus 1. So that's not a problem. Okay? Just like I have, I'll write down here. 3 to the power of k plus 1 is 3 to the power of k times what? Okay, this is something you do in grade 9, huh? 3 to the power of k plus 1 equals 3 times?
3 times 10 to the power 1.
Yeah, or 3. Okay, so it's the same thing we're doing now. But instead of 3, I've got this cosine theta plus I sine theta. Okay, so cosine theta plus I sine theta power k times cosine theta plus I sine theta. Okay, I'll just pause here. That was actually the hard bit. It's that how you split it. Okay, when we had the sum, we split it something plus something plus something, sigma plus okay? Now when you have a multiplication, it's something times something, it's actually easier. Multiplication seems to be easier. Now it's easy, but it's messy. Now it's the messy part. Okay? Or actually, sorry, there's one more crucial part. What can I do now with this business?
You can use your...
That's the tool. Okay? So now we're going to write, I'll try and squeeze it here. Instead of that, I'm going to write this. I'm going to write cosine k theta plus I sine k theta, putting brackets on this, time that. Cosine theta plus I sine theta. In this case, now we're just doing normal algebra. Okay, so we multiply that and that. Maybe you guys can tell. What's the first two? Cosine k theta times cosine theta, right? that, time that. Okay? With me? We time that by that, plus that by that, plus that by that, plus that by that. Okay, so what's the next one? It will be still cosine k theta. Now you guys gotta tell me. Cosine k theta time? Come on guys, multiply. That times that. So time I sine theta. Okay? Okay? Do you mind if I put the I in front? It's like I is like a number. So I'll write I cosine k theta times sine theta. Okay? Right, you are going to do the next one. What's the next step? I sine theta. I'm cos k theta. Okay? And the last one? Plus? So I've got I sine theta times I sine k theta. So can I have I squared?
Yeah.
Sine k theta. Okay, before I do anything else, what can I do with I squared? Okay, so we did say I rubbed it, but we said that I is red. Okay? Okay? Yeah? I is equal to square root of minus 1. So what is I squared? Minus 1. That's the definition of I. It's the square of this imaginary number is minus 1. It's not a real number. And we're dealing with the whole next week. So instead of I squared, I'm going to write minus 1, right? In other words, minus that. Okay? Now, at this point, I'm going to pause because I need some space. Okay, so now what I want to do is, you can look here, I've got 4 terms. 2 terms without the I, that one and that one. And then 2 terms with the I, that one and that one. And that means we're in a good direction, because if you look at it, what we want to prove is there should be something with I and something without I. So I'm going to separate them. Okay, I'm going to write that here. First I'll start with the one without the I. So I'm going to have cosine k theta, it's this one, times cosine theta, minus this one, sine theta, sine k theta. Okay, that's the first term. And then I've got plus I, going a little bit skew here, sorry. These are the 2 i's, they were in the middle. So I'm going to put I out of brackets, because that's like a common factor. And I'm going to have cosine k theta, sine theta, plus, do you know what, actually I want to change them around. So I'm going to change it to, instead of cosine k theta times sine theta, I'm going to call it sine theta times cosine k theta, right? You won't mind if I replace when I have the product. It's the same thing. 2 times 3 is 3 times 2. Plus sine theta, no, hang on, that's exactly the same. I think I made a mistake. Let me just pause here for a second. I've got an identical. All right, so we obviously, I just noticed that these 2 terms, if you look at that term, cosine k theta, sine theta, cosine k, they're the same, and we shouldn't have the same term. Okay? I know where I'm going, that's why I know it's something wrong, and I did actually make a mistake. This term is incorrect. This term was supposed to be that times that. So it should be sine k theta times cosine, sine k theta times cosine theta. That was just a mistake. Okay. Okay? So therefore, I wrote, I'm confused, sine theta cosine k theta, that's this one, plus, now it should be cosine theta sine k theta. That should be right. And that is in brackets, square brackets. Again, I'll stop here. Okay, so let's just review again where we're standing. There is a slight hiccup, not a hiccup, but this term, sine theta, sine k theta, Really, I should have written sine k theta times sine theta. Obviously, it's the same thing. So that's not a problem. Obviously, we have a mistake here, but we corrected it. It's all good. What we're actually trying to prove, it's good to once in a while remember what we're trying to prove. We're trying to prove that this is equal to that. We want to prove the radius. So we started from here, and look, we're almost there. We have something without I plus something time I, just like that. So you can see what we really need to prove now. We need to prove that this bit, cosine k theta minus sine theta sine k theta, really is cosine k plus 1 sine theta. And we want to prove that the sine, cosine, sine is the same as sine k plus 1 theta, because it has that I, just like this. Right? Now at this point, you haven't done this level of trig, so you wouldn't know it, but you will learn it very soon. Okay? We use this trig identity. This trig identity tells you that if you have cosine, a sum of angles, a cosine of the sum of angles, cosine A plus B, unfortunately it's not cosine A plus cosine B. That would be really easy, isn't it? Instead, is cosine A times cosine B minus sine A sine. And then we have a similar but not the same one for sine A plus B. Again, unfortunately, it's not sine A plus B, sine A plus sine B. It's sine A cosine B plus cosine A sine B. I'll pause here, there's a question. Okay, so I can see that I was listening. That's good. That's good. Okay, so look at this. What do I have here? I have a cosine, we'll call it an A. A is like k theta times cosine B minus sine B cosine A, sine A. So I've got a cosine minus sine. That's just that. That's just that. So I'm working using this trig identity in reverse. If I have a cosine A, cosine B minus sine A, sine B, I can write that cosine A plus B. So my A we said is k theta, my B is theta. So what I'm going to write down, I'll write in blue because it's like the final thing. Instead of that, I'm going to write cosine A plus B. What is A plus B? Is k theta plus theta. Right? That was A and that was B. And see where we're going. Plus I. Okay, in I have sine, cosine, cosine, sine. Sine, cosine, cosine, sine. That's exactly the sine trig identity. So again, I'm going to work in reverse. Now in this case, I'll call this A and I'll call this B. That means that's A and that's B. So sine A cosine B plus cosine A sine B. We're going to write it as sine A plus B. What is A and what is B? Theta plus k theta. Notice that here, I call this one A, I call this one B, and this one A, and this one B. It doesn't matter. It actually worked out. Okay, as long as I'm consistent, it worked out the same. Now we're almost there, isn't it? What do I have to just do now? Because where do I want to go? I always look, where do I want to go? I want to go to there. K plus 1 times theta. Can I do something for this k theta plus theta? What can I do in the bracket? What can I take out? The theta, take it out. Now I'll have time k plus 1. Hey! Got it. We got the water. We got it. I'll put k plus 1 instead of 1 plus k. Okay, so we proved the moire using induction. Okay? Alright, well done.